and welcome to the module DC Motor Basics. In this module, we're going to be going over the robot platform DC motors. Each robot you use will have two DC motors. We're going to go over how do we estimate the parameters in these motors so that we can build a control system around them and get them to do exactly what we want. The DC motors that we use on our robots use an optical encoder to translate motor rotation to frequency, a series of pulses at a certain frequency that we can use to determine how fast the motor is going from a microcontroller or some other device. The motors themselves will model with an equivalent circuit, which you should have seen in class and which we'll go over in a little bit more depth slightly later. We also have a gearbox on each of these motors, which changes the ratio, giving us slightly more torque on the output. Finally, of course, there's a wheel on the motor so that the robot can actually move. We're going to spend most of this module going over the internals of our DC motor in terms of how do we estimate the parameters that make up the equivalent circuit so that we can have a very high accuracy model of this to build a control system for later. We're going to model our DC motors using this two-part equivalent circuit you can see here. Hopefully this came up in class as well. Now the left side of this equivalent circuit is an electrical equivalent model. And this model is the input port to our DC motor. You can see we have some applied voltage and some resulting current going through our motor. This is the electrical side of our motor equivalent circuit. On the right hand side we have the mechanical model of our motor. And you can see we've drawn it just like a regular circuit diagram, but you'll notice that we actually have torque, T, as our analog to current, and we have omega, or angular frequency, as our analog to voltage. So it's a little bit of a shift in thinking, but just remember that you can still analyze it just like a regular electrical circuit. It's just that the quantities have slightly different names. The next few slides we're going to go over how do we estimate all the parameters in these equations, Rm, Lm, K, and we have B and J over on this side. Now these all have physical meaning to our motor, and we'd really like to nail down what their precise values are for the individual motors so that we can have a very accurate model that we can put into simulation and that we can design control systems for later. Now the first parameter we're going to try and estimate, and probably the easiest one, is Rm. We'd like to find out what value is this resistance. Now, there's a number of different ways to do this, but the easiest is just to recognize that if we simply apply a DC voltage here, and we don't let that change, we're going to have a DC current coming through this circuit. With a DC current through the circuit, this inductor is going to look like a short, and so that's going to remove it from our circuit. Additionally, it's going to remove it from our equations. Finally, we can notice that VEMF is directly proportional to the motor rotational speed. So if we can simply set omega to 0, this source is going to go away as well, and you can see we now have just a resistor between our input ports. Now how do we set the rotational frequency to 0? Well, you can simply hold the motor wheel to stop it from rotating. That'll set it to 0. You'll have some current that you can read off of your power supply, and that'll be because of some applied voltage. See, this drops away to 0, and now we have this very simple equation. And you can just write Rm is going to equal the voltage you've applied over the DC current. Now, it's a good idea to take this at 2 or 3 different voltages. Should be resistance, so you should get approximately the same value each time, but then just average the results to make sure there wasn't any measurement error. And that's how we're going to estimate Rm. It's really the easiest parameter to estimate for these motors. The next parameter we're going to look at is K. K gives us a ratio between our angular frequency of our motor and the voltage seen on this VEMF source. So really what K does is it gives us a relation between our mechanical side model and our electrical side model. Now let's just take a look at the electrical side of our model, and if we were going to estimate K, what are some of our unknowns? Well, we don't know what Lm is, But we can solve that, again, like we did for estimating RM, if we only apply DC voltages to our input. So let's assume we're only going to apply DC voltages, and we can cross out LM, make that into a short, and we can remove it from our equations down here. Additionally, we have RM sitting right here, but fortunately we estimated RM in our first step, so that's really well known as well. Finally, we have our input voltage and current, but those are easily measured using a multimeter. And our last parameter we don't know is really this omega. What is the angular frequency of the motor? Well, if we hook up one of our encoder outputs to an oscilloscope, you can simply measure the frequency of omega, and that'll give you that parameter. What that leaves us with is a single unknown on this side. We simply have K. So, how do we determine what that value is? Well, we can rearrange these equations down here in terms of K, if we want to, so we can simply write K, and we have omega times K is going to equal VDC minus RM IDC. And what we can do is we can simply toss omega onto the other side. So we have K equals VDC minus RM IDC times 1 over omega. Now, again, just like when we measured RM, don't take a single point. You're going to have to take multiple points and then average them to find out what your K value is. For each voltage you input, there'll be an associated current that you can measure and an associated angular frequency you can measure. And when you're doing this, be careful. This is angular frequency in radians per second, not hertz like you'll read from the scope. So make sure that you have the translation there. And what you should end up with is in Excel or some other spreadsheet program, a table of VDCs and their associated IDCs and omega. You can use the RM that you estimated from the first step, and you'll have a number of different values for K that'll come out just because of measurement noise. So average all those values, and you should get a fairly good estimation of what our K parameter is. So at this point, we've really estimated almost all the parameters on our electrical side of the model. We know what RM is, we did that the first step, and additionally now we know what K is. And so if we operate at a DC input voltages, you can see we can now directly relate VDC to our mechanical side of the motor. That is, we can operate with constant inputs and we can ignore this inductor. And that removes him from the equation. Now we'd like to estimate some of the parameters on our mechanical side of the model. And you can see that if we're assuming we're operating at DC input voltages, that's going to make this current constant. If that current's constant, you can see we're going to have a constant torque here simply because of this relation. If that's constant, then we can ignore this capacitor. So let's just get rid of him. And that means we can also cross him out from the equations. I would like to simplify things a little bit more. And you can see T load here equals the sum of just the internal torque. So that's whatever resistance the motor provides itself. How hard is it to just turn it without a load, and the external torque. Well, let's assume we don't have any external torque. That's going to mean T load is just equal to T internal. It's going to simplify things a bit. Now you can see immediately we have an equation with two unknowns. How are we going to deal with that? Well, let's just write this out a little bit clearer, and we're going to substitute K IDC for T, and we're going to substitute T int for T load. So we have K IDC equals B omega plus T int. We know what K is, so let's just divide through by that. And now, what does this look like? Well, we have our input IDC equals B times what we'll say is our output, so omega, plus T int. This looks a lot like the line or the equation for a line, right? We have a slope, our slope is B, and we have an intercept, T int. So if we were to simply take a number of data points, where we have IDC related to omega. We could plot those, and what we should end up with is some line going up where we have some intercept, which is going to be our T int, and some slope, which is going to be our B. So we can do that pretty easily in Excel. In fact, if we took enough data points from our previous step where we estimated K, we should already have all these measurements taken. We don't need to take them again. And from this we'll get two of our parameters. We're going to end up with B and we're going to end up with T int. Now, two things to make sure you're careful about here. The first one is you have omega, which is again angular frequency, so that's radians per second, not hertz. Be careful about that. Additionally, we have this scale factor on the end, so make sure you're multiplying everything by that. And that's pretty much it. Plug these into Excel and you should get a good measurement of what B is, which will give us this value, and what T int is. Now the last parameter we're going to try and estimate is this J parameter, which you can see over here gives us some of the dynamics on our mechanical side of the model. J is a little bit trickier to measure than any of our other parameters so far. And this is mostly due to the fact that it is a dynamic parameter. So if we just did like we've been doing and have a constant VDC input, then we're going to have a constant IDC, so a constant current running through this wire. And a constant IDC is going to give us a constant here, which is simply going to remove this capacitor from the circuit. That's not at all what we want. So, because we can't use a constant input to determine J, we're going to use a dynamic input. And there's two easy ways to do this. The first one is to have a turn-off transient, and the second is to have a turn-on transient. What does that mean? Well, you can hook this motor up and then just turn on your voltage source and measure what the outputs do, or you can hook it up and just turn off the voltage source and measure what they do. Now, a turn-on transient is a little bit tricky, and this is mostly because we don't know exactly how these voltage supplies are going to turn on. If you've measured transient turn-ons with your voltage supply before, you know it doesn't just jump up to whatever voltage you set it to. There's some ramp up and some slow dynamics, and we really don't want to have to deal with that. So we're going to do a turn-off transient. What does that mean? Well, if we have time down here and VDC up here, and if we just go along, here's our voltage, and then at some time we just turn it off. What we should see is our voltage starts to slowly sort of drain away and ramp down as soon as we turn it off. When you turn off these supplies, they simply open circuit their output, and so we end up with an open over here. Now, what does that do for us? Well, if we've open circuited this, we no longer have a loop for current to flow in, which means IDC is 0, right? We've open circuited this, so at this point, right here where we turn off, IDC is now 0. Because IDC is 0, we can ignore RM. In fact, we'll ignore this as well, which means VDC is now going to be equal to EMF. Alright, let's remove these things we don't care about from the circuit. IDC is 0, the derivative at 0 because it's just a constant value at 0. Then we have VDC equals VMF. Additionally, on the mechanical side of our model, you'll notice if IDC is 0, then this is 0. So we can get rid of him. If we have a current source which has 0 current through it, that's just an open circuit, so this is open as well. And we can remove this from this side of the equation as well. IDC is 0. And we're going to use the same estimation where we have no external torque. So we're going to cross T external out. And you can see we've simplified things quite a bit here. Now let's take a look back at our plot after we've done all these simplifications. Because we now have that VEMF is K omega, and that our VDC is just equal to VEMF, we can see that this plot could really be, instead of a plot of VDC, it could be a plot of K omega. And if we just scaled things, what we really have is a plot of our frequency omega versus time. So we have omega versus time over here if we just scale by k. Okay, so let's zoom into one specific part on this plot. Let's just, pick this location and let's zoom in a little bit. Well, it's going to, unexcitingly look like a diagonal line if we just zoom in straight enough, and it's going to have some slight curve to it. Again, we have time going this way, and we have, now that we've scaled properly, we have omega going this way. So this is just a zoom in of that portion. Well, what can we do with this? Let's pick 3 points on this plot. Let's pick a point there, and a point there. Well, if we measure between this point and this point, there we have a dt, a little time interval. And if we take a look at the other axis, there we have a d omega. And if we take a look at sort of the average, the middle, that's just a steady state omega. Okay, what do we do with these? Well, plug them back into our equation. Take a look up here. We've given ourselves a d omega, so that's a known. We've given ourselves a dt, so that's a known. We've chosen an omega in the middle, so we know that. B we've already estimated, and t load is now equal to t int, and we know what that is. Our only unknown is this j parameter. So you can imagine that if we just select a number of different points, for instance, let's select maybe 5 or 6 points along this curve, and we have this up on our scope because it's just VDC we can measure, and we just selected each of those areas. We select 3 different points, an upper, a middle, and a lower. From each of those we can find a dt, a d omega, and an omega. We can plug those into this equation along with the parameters we've already estimated, and we can use those to get an estimation for our j parameter. So do that a few more times, put it into an Excel spreadsheet, and you could get a pretty good estimation of j. Now once we've gone through that and figured out what this j parameter is, that really completes our model. We know j from this transient test. B and t internal we know from our second experiment, and Rm we know from the very simple first experiment. Additionally, Km we've determined. So that fills out all the parameters we care about in our model. Really the last thing we need to look at is how does the encoder work? And once we've figured that out, we'll have a complete model of this motor that we can input into a program like Spice. Now the optical encoder is really a fairly simple device. Physically, then we have this wheel which is attached to the motor shaft, which has a number of different slots in it. And there's just 2 LEDs and 2 photosensors on the other side of this. And so as it rotates, the light, hits and then doesn't hit the photosensor, and you end up with this sort of square wave coming through your optical encoder. And you can imagine if this, wheel is turning slowly, you end up with sort of a slow square wave, and if it's turning fairly quickly, you end up with a fast square wave. So that works, but it doesn't really tell you which direction this thing's turning. So to do that, what we actually have is 2 sensors and 2 LEDs, and you can see they're just placed very close to each other so that one will get hit with light before the other. And what you can do with this is you can see, depending on the direction of rotation, for example, if you look at the falling edge of encoder A, if we're going counterclockwise, falling edge of encoder A is going to happen when encoder B is high, and if we're going counterclockwise, falling edge of encoder A happens when encoder B is low. So you can determine direction based off of that. There's a fairly simple way to go from angular frequency to a frequency that we can measure with a scope or that we could determine with a microcontroller. And once we've figured that out, we can go back to our full model of the motor, and you can see we now know all the parameters in here. We know directly how VDC relates to motion on the gear shaft. And then additionally, we now know how motion on our gear shaft relates to our optical encoder. So we now know all the parameters to relate input voltage to the frequency read on our encoder. Now, we can enter all these into LT-Spice, and really only non-standard thing is that, remember, omega looks like a voltage, and we're going to model it as a voltage in LT-Spice, but really it represents angular frequency. Additionally, the torque going along these wires is a torque, but it looks like a current, so in Spice we're going to model it as a current. And you'll be able to download this model from the website. The slightly more complicated part of it is just this encoder model, but we've made that for you. It's a fairly interesting circuit to generate these pulses, which depend on frequency of the motor shaft. So you can see we have this equation down here to do that, dependent on this V omega, or this angular frequency. If you want to go through that a little bit, try and figure out what it does, it's fairly interesting and useful. But anyway, enter in the parameters that you've estimated. You can see RM, K, J, B, T, N. Those are all things that we decided on. We'll give you the value of LM, which we've ignored throughout this whole thing. And you can now simply run a simulation of the motor. And if you were to do that, you might get a plot like this. You see we have V omega. It thinks it's a voltage, but really we know it's an angular frequency, so make sure you scale accordingly. And there we have our turn on transient and turn off. You can see our encoder pulses in kind of teal down here are nicely generated from that separate block. And we have things like our motor current, what's the DC input voltage, encoder pulses. Now you can use this to compare to your physical motor. So just turn it on and off again and see, does it match up to the model. That's sort of how we estimate all the parameters, and that really completes the model of our motor and how we make it work, how we get a Spice simulation from it.